I wanted to talk about problem solving in physics, just to offer a little advice on problem solving in physics. And so we're going to work through a sample problem. And I'm going to try and describe the thoughts that go through my head as I work through that problem, the steps that I go through as I work through this sample problem. Before I do that, let me just ask a question. The question is, how did you learn to ride a bike? So did you learn to ride a bike by watching your older brother or your older sister ride a bike, and then suddenly you could ride a bike? Probably not. Did you learn to ride a bike by taking some advice from your mom or taking some advice from your dad, and then suddenly you're able to learn to ride a bike? You probably didn't. You learned to ride a bike by practicing to ride a bike, by trying to ride a bike. So you probably fell off a number of times, and then with practice and more practice and more practice, you fell off less and less. And ultimately, you were able to ride a bike without really thinking about riding a bike, without consciously thinking about riding a bike. So that type of learning how to ride a bike, where you practice, train yourself to ride a bike, is called experiential learning. The type of learning where you watch your brother or your sister riding a bike, or you listen to your mom or dad's advice on riding a bike, that's called observational learning. Solving physics problems is learned best in a similar way to learning to ride a bike. It's best learned by practicing to solve physics problems. It's best learned by experiential learning. Experiential learning is more personal. So you're more invested in experiential learning. You're more engaged in experiential learning, rather than if you're just listening to somebody rattle on about how to solve a problem. If you're trying to do it, you're much more engaged. Still, though, it's not unuseful, not useful for me to offer you some advice on problem solving. And so I'm going to go ahead and offer a little bit of advice by way of how I would solve a problem, how I would solve a sample problem. The problem I'm going to solve is depicted in this little picture here. We have a magician, and we have the magician's audience. And the magician shows the audience an amazing trick. And in this amazing trick, he suspends two small balls from two thin threads. And these balls are held in his hand, and they hang at a gravity-defying angle that is not vertical. And everybody's astonished. Everybody's amazed by this trick. What the audience doesn't know, what the audience doesn't realize, is that the magician rubbed those balls to charge those balls before the trick. And so that those balls not just experience a downwards pull of gravity, but they're also experiencing a repulsive force from electricity. And so that's the reason the two balls do not hang vertically. They hang at some other angle. And now, to make the problem quantitative, we're told specifically that in this trick, these small metallic balls, they have a mass that's 0.04 grams, so they're very light. The strings in this particular problem, they have a length that is 34 centimeters, 0.34 meters. And the two strings, they hang from a common point at an angle that's 7.3 degrees away from the vertical. given that information for us to figure out, for us to compute how much charge is on those two metallic balls. The one on the left, how much charge does it have? The one on the right, how much charge it has, under the assumption that they both have the same quantity of charge and same sign of charge, so that there's a repulsive interaction between them. And so our task is to find that charge. So when I read the problem, I start to make an image in my mind, kind of mental image of the situation, of the physics situation. So in this mental image, I'm restricting the image to the things that are important from the perspective of the physics problem. So I'm restricting the image to the balls that are hanging, to the strings that they're hanging from, to the geometry of the strings and the balls. But I'm ignoring superfluous stuff like the magician and like the audience and the amazement and the applause of the audience. That's all irrelevant. I'm also very conscious of the things that we were told in the question, things like the mass, the length of the strings, other things too, and the thing that I need to find in the problem. So that's the charge. Another thing about my mental image, it's sort of framed. It's a framed mental image. It's framed by the physics context of the physics problem, or the physics principles surrounding the physics problem. So when the two balls are hanging from the two threads in space at rest, the guiding principle for solving this problem is going to be that those two balls are in equilibrium. That means that there are forces acting on those balls, but the sum of those forces adds up to zero. And so they're in equilibrium. They're not accelerating or decelerating. They're at rest and staying at rest. That's a real physics principle, a real physics context for this problem. The other bit of physics principle, physics context for this problem is, what are those forces that add up to zero, that combine to zero? Well, we said that obviously the balls are pulled down gravity. Obviously, the balls are experiencing tension from the strings. And then that third force is that electrical force between the electrically charged balls. So the balls are experiencing gravitational, electrical, and tension forces. That too is part of the context of this problem. Finally, my image, my mental picture of the physics problem is abstracted from real life. So, for example, the small metallic ball, I'm just picturing it as a point mass ball. For example, the thread, the string, I'm just picturing it as an unstretchable, massless string. And so those are some abstractions of the ball and the string, of the players in the physics problem, that will actually help me solve the physics problem, help me focus the physics problem. So I'd like to be able to just sit here and tell you how it is I knew what's important and what's not important in this problem, and how I knew what the principles were, what the concepts were for this problem, and how I knew, to abstract the ball, to abstract the string in this problem. The problem is that a lot of that is just unconscious. So I believe my knowledge of what's important, what's not important, the principles, the concepts, the approximations, the simplifications, just come from experience of solving and practicing many, many problems over many, many years. And so that unconscious recognition of what the problem is about, what the approximations, simplifications are, is what comes through experiential learning, is what comes through practice and practice and practice. And it is like riding a bike. It becomes habitualized. It becomes unconscious. If you're stuck with figuring out, say, the concept or the principle behind a problem, you might want to think about, well, what's the question telling us? Does it tell us of force, an energy, a field, a potential? Or, what's the question asking for? Does it ask for a charge or a current or a frequency or a wavelength? Those are all clues. Those are all cues to the foundations or the concepts or the principles beneath that problem. So my next step, an important next step, is to make a sketch with pen and paper of that physics problem, of that mental image that I've just constructed. Now, my sketch is going to incorporate the relevant objects. So that's, the ball and the string and the geometry. It's also going to incorporate the relevant concepts, ideas, principles. So that's, equilibrium and the various forces. In making the sketch, you're really crystallizing and clarifying your ideas and your reasoning about the problem. To make that sketch, you've really got to resolve, reconcile any uncertainties, any ums and ahs about what's happening in the problem. And so that's very important. So let me go ahead and make the sketch. Okay, so here's my sketch. The red line in the center here is the vertical. And upstairs here on the vertical is the common point that the two strings are attached to and the two balls are hanging from. And so we see the string on the left, string on the right, the ball on the left, and the ball on the right. So that's the basic geometry of the problem. I've added to that sketch some facts that we're told in the problem, some values for quantities that we're told in the problem, and also some understanding of the problem. So from the point of view of the quantities that we're told in the problem, here's the length of the string, L, 0.34 meters, so I denoted that. Here's the angle of the string, 7.3 degrees. I've denoted that. I could have added the mass of the string, of the ball, that's 0.04 grams. It's another quantity that we know. And then I've also calculated, because it's going to be useful, this separation between the two balls, between the two charge balls. You can get that separation from a little bit of geometry of a right angle triangle. There's one right angle triangle on the left and one right angle triangle on the right. And the length of this opposite side of the right angle triangle is given in terms of the hypotenuse of the right angle triangle, which is the string, as L sine theta, where theta is the angle in the triangle. And because I've got a triangle on the left and a triangle on the right, separates the ball on the left and the ball on the right, then the total separation of these two balls is going to be 2L sine theta. And it's 0.086 meters. I computed it. Anyway, that's part of my sketch. Also on the sketch, I've got the fact that there are three forces acting on each ball. Now, I've only drawn them on the right hand ball and not drawn them on the left ball, but it's the same pattern on the left as it is on the right. So there's one force, gravity, that's vertically downwards. That's this vertical arrow here that indicates the approximate strength and the direction of the force. There's a second force, tension, that's acting on the ball. That's this green arrow, angle green arrow here. It's acting at an angle to the vertical. It's acting along the string. And then finally, there's this third force here. This is the magic in the magician's trick that amazes the audience. This is the electrical force. This is the electrical repulsion between the two balls. And so I've indicated that fact here. And I might also annotate my sketch with the sort of master equation for the problem, that the sum of the forces on the right-hand ball is 0, and the sum of the forces on the left-hand ball is 0, because this is a situation of equilibrium. So it's really by making that sketch, as I say, I sort of crystallize and quantify my understanding of the problem, my understanding of the situation that's going on here. So my next step in solving this problem is to turn this sketch and this image of the problem, both the objects involved in the problem and the concepts, principles behind the problem, to turn that into equations that describe the problem. Now, normally this starts with, almost always this starts with, kind of a core equation, a very fundamental equation, a very basic equation that's describing the problem. So in this particular case, the core equation, the core idea that's at the heart of this problem is that of equilibrium. And what equilibrium means here is that there are forces acting on the ball, but those forces add up to 0. And so that's really the starting point for my solution to this problem. So I'm going to write that down. And so here's my statement. The sum of the forces acting on, say, the right-hand ball add up to 0. And that's equilibrium. Now, that equation would be relevant to dozens, maybe hundreds of problems in physics textbooks, right? In many physics textbooks, there's literally hundreds of problems involving equilibrium of forces. And so this is really a core equation, a master equation that would describe many, many problems in many, many physics textbooks. What we've got to do now is take this most basic equation, this kind of foot in the door equation, and we're going to turn it into an equation that's specific to our problem. And by doing that, that'll lead us into solving our particular problem. And so what I'm going to do is kind of expand outwards this basic equation into an equation that is specific to our mass on a string problem. So the first thing is that there are 3 forces in our case that add up to 0. So there's a gravitational force, an electrical force, and a tension force. So I'm going to expand that master equation to indicate that. And then the second thing is that these forces are vector quantities. So vectors have sizes and directions. And so when we say the sum of the forces is 0, it's the sum of 3 vectors in this case that is 0. And so I'm going to write down that sum in terms of the fact that in the vertical direction, the forces must add to 0. Their components must add to 0. And in the horizontal direction, the forces must add to 0. Specifically, the horizontal components must add to 0. And so that's the second way I'm going to expand the master equation for my particular problem. So let me write those 2 things down. Okay, so here's my expansion of that master or core equation of equilibrium into the specifics of my particular problem. So let's just walk through these equations here. So the first thing I identified or recognized was that the sum of the forces in my particular problem, in my particular case, is the sum of the gravitational force, electrical force, and the tension force on a ball. Those three forces add up to zero. So that's the first idea that went in. The second idea that went in is that when we say that the forces are in equilibrium, that the sum of the forces is zero, it means that because the forces are vectors, because they have sizes and magnitudes, we can think of it as the sum of the x components, horizontal components of the forces, must add up to zero, and the sum of the y components, the vertical components of the forces, must add up to zero. And so in this case of equilibrium of forces, there's an equilibrium in the x direction and an equilibrium in the y direction. That's what I'm denoting here. The sum of the forces in the vertical direction must add up to zero, their components. The sum of the forces, their components in the horizontal direction, must add up to zero. And so I wrote that equilibrium in the vertical direction out in this equation I labeled 1. I wrote that equilibrium in the horizontal direction. In this equation here, I labeled it 2. Let me just go through these two equations. So, equilibrium in the vertical direction. There are two forces, not three forces, that have non-zero components in the vertical direction. Gravity has one, it's pulling downwards, and tension has a component that's pulling upwards. You can see it in the picture here. This angle here is theta. And so in the vertical direction, there's gravity downwards. I call that the positive direction. And there's a portion of tension upwards. That's the negative direction. And those two pieces must add up to zero. And so that's why there's just two terms here in the vertical equilibrium. There's a similar thing for the horizontal equilibrium. In the horizontal direction, again, there's just two forces that have non-zero components in the horizontal direction, not three. So the electrical force is acting horizontally, and so that has a component horizontally. The tension acts at this angle, so it too has a component horizontally. And so we see two terms, one for tension and one for the electrical force. The electrical force is acting towards the right. So that's the plus sign here. I call to the right, positive. And so the tension force, you can see it's acting in the other direction, horizontally, towards the left. That's the negative sign here. And so that explains why my equilibrium in the horizontal and vertical directions, in each case, in this particular problem, just involved two of the three total forces involved in the overall equilibrium. Now, let me say a few more things about how I wrote gravity in the vertical equilibrium, how I wrote electricity in the horizontal equilibrium, how I wrote the components of tension in the horizontal and vertical equilibrium. So for gravity, the gravitational force, called it Fg, is equal to mg, the mass of the body times the acceleration of the gravity. So I filled in here, again, tailoring the equation to my particular problem, the expression for the gravitational force, mg. I did a very similar thing with the electrical force. The electrical force, Fe, I've written it in terms of Coulomb's law, how that force works. So I wrote it as K times the charge, the product of the charges on the two spheres, divided by the separation square between the two spheres. And so that's me expressing not only the electrical force, but how it depends on the separation of the charges and the amounts of the charges. And then finally, tension. I don't actually know immediately what the tension force is, but I do know it's split into vertical and horizontal components determined by the cosine and the sine of this angle of the string. And so that's why I wrote t cosine theta here for the vertical component, t sine theta here for the horizontal component. Those are the portions of the tension force in the horizontal and vertical directions. And so equations 1 and 2 are really now I work my way from the core master equilibrium equation, sum of forces 0, to a pair of equations that incorporate all the features of my problem. 3 forces, gravity, electricity, tension, and how those forces are working in this situation. Newton's, the law of gravity, mg, the Coulomb's law for electrical forces, kq squared over r squared, and tension being broken, separated into horizontal and vertical components. At this point, the problem has kind of changed from one that is physics-centered and based on physics principles, physics understanding, to now one that's more algebra-centered and based on our skills, abilities in algebra. At this point, we've got 2 equations based on equilibrium in the horizontal and vertical directions, and we want to solve those equations for an unknown quantity, Q, the charge. And so that's our job, that's our algebraic job. Now, in the algebra part of physics problems, sometimes you're faced with just one equation from one core concept, one core principle, and just a simple rearrangement of that one equation to obtain the unknown variable parameter in terms of known variables parameters. In other problems, this is an example, you're faced with more than one equation and a more complicated process, more complicated algebra of extracting the interesting unknown from those equations and the knowledge of the other parameters in those equations. So what we're going to do here is some sort of combination of rearranging these equations or putting one of these equations into the other one of these equations, and then solving these equations, rearranging these equations for the unknown charge. So specifically, what I'm going to do is I'm going to take equation number 1, and in a way, I'm going to kind of insert it into equation number 2. My goal here is to replace the tension in equation number 2 with the expression for the tension that I can get from equation number 1. So if you look at equation number 1, I could rearrange this equation for tension. T would be equal to mg divided by cosine theta. I could then take that and insert it into equation number 2, replacing T in equation number 2 with mg divided by cosine theta. And so let me go ahead and do that, and we'll end up with one modified equation, and we'll see the power of that one modified equation, that one blended equation that's going to allow us to solve for the charge. So the first term is going to be exactly the same in this new blended equation. kq squared over r squared. The second term, that's going to be different because I'm going to replace the tension in the second term with the expression for the tension from the first equation. So I'm going to get an mg, and then I'm going to get a division by cosine theta. I'm going to be faced with sine theta over cosine theta. That's tan theta. And so I'll simplify that. And so this is the blended equation. This is an equation that combines the 2 equations from the equilibrium and horizontal directions, eliminating the variable t, eliminating the unknown tension. And now, if you look at this single equation, it contains the charge. That's the parameter quantity I want to figure out. But all the other quantities, parameters, k, R, M, G, theta. There's a whole list of them. They're all known to me. And so all I have to do now is the algebra of rearranging this equation for the unknown parameters Q in terms of the other known parameters. And so let me go ahead and do that. Basically, this is a matter of, if you think about rearranging. What is rearranging? It's like playing with weighing scales, mathematical weighing scales. If you have an equation, think about quantity on the left-hand side of the equal sign, the quantity on the right-hand side of the equal sign. Think about the analogy to weighing scales. On weighing scales, you can add on to both sides of the scales an equal quantity, still in balance. And the same thing for a mathematical equation. You can add on the same quantity to the left and right-hand sides, and it'll stay in balance. You can subtract off too. You can multiply too. You can divide to the left-hand side or right-hand side by the same quantity, and the equation, the weighing scales, stays in balance. And that's all I'm going to do here. If I add on mg tan theta to the left and right-hand sides, that effectively moves mg tan theta over to the right-hand side. If I divide through by k, that will move k to the right-hand side. If I multiply through by r squared, it will move the r squared from the left-hand side to the right-hand side. And in that way, I can isolate q squared and then take the square root to get q. And that's all I did here. I'm just going to write it out. Q equals r times the square root of mg tan theta divided by the constant k. And so that's the equation for the unknown charge in terms of the known quantities r, g, theta, and k, the Coulomb constant. I won't bore us with plugging in all the numbers, but if you do that, 6.4 nanocoulombs, 6.4 times 10 to the minus 9 coulombs is the answer. Well, this is the solution to our problem of the magic trick and the equilibrium of the three forces, gravity, tension, electricity. The charge is 6.4 nanocoulombs on the left hand and the right hand ball. That creates a repulsion that causes the two balls to not hang vertically, but hang at 7.3 degrees. At this point, I'm going to pretend to be your aunt, and I'm going to offer you some advice. So what is the advice I want to offer you about problem solving? I want to offer you a few pieces of advice. One of them is to do what I just did in terms of working as much as possible in terms of symbols for quantities rather than the numbers for the quantities. I left the use of numbers to the very end of the problem. The reason to do that, sometimes we're scared of that because that's algebra. Working with symbols is algebra. Working with numbers is arithmetic. We met arithmetic when we were 2 years old. We met algebra when we were in high school. So it's a little scarier to work with symbols than numbers sometimes, but it's actually much safer to work with symbols than numbers. See, symbols, the symbol carries the meaning of the quantity. And so it's easier to trace what's going on. It's easier to understand what's going on. It's easier to fix problems with what's going on if you use symbols. Numbers are completely agnostic. They don't tell you anything about whether this is a force or an energy or a charge or a current. They're just numbers. So they're very hard to trace, to follow through a problem. So first piece of advice, use symbols as much as possible. Leave your numbers to the very end of the problem. Second piece of advice. Second piece of advice is about checking your answer. it's worthwhile and it's actually important to check your answer. We got an answer of 6.5, 6.4 nanocoulombs, and we got that answer from that equation that the charge is equal to r, the distance between the two charged spheres, times the square root of mg tan theta over the Coulomb constant. So one way you can check an answer is, does the number that you got make some sense? So to give you another example of this, supposing that a problem asks you to calculate the mass of an elephant. If when you calculated the mass of an elephant, you got 2.5 grams, you'd know that that was ridiculous. An elephant is much, much heavier than 2.5 grams. So it would tell you that there's some mistake, some problem in your solution. If you were calculating in your problem the height of a skyscraper, and calculated the height of the skyscraper, and you got an answer that is 2.5 centimeters, well, you would know that that's ridiculous. A skyscraper is much higher than 2.5 centimeters. So you would know that you've made a mistake somewhere. There's something wrong in your solution. So checking the number makes sense is an important thing to do when you've completed your calculation. Now, sometimes that requires a bit of experience. So I know from experience that when you charge things by rubbing, then the sort of charges you get are nanocoulombs or microcoulombs, very small fractions of a coulomb. So this number does make sense. If I got an answer that was a coulomb or 1,000 coulombs or millions of coulombs, I would know that that would be ridiculous. You cannot charge by rubbing to a coulomb or 1,000 coulombs or 1,000,000 coulombs. Another question that you can ask about your solution is, does that equation that we use to calculate the charge, does that equation make sense? So there's lots of ways you can ask whether the equation makes sense. That depends on the particular equation and the particular problem. But let me just give you a couple of examples. So suppose that we increase the mass of the two spheres. That would increase the gravitational force on the two spheres. For the two spheres to hang at the same angle, therefore, we'd have to increase the electrical force between the two spheres, the electrical repulsion between the two spheres. And that means we would have had to increase the charge on the spheres. So that reasoning is tied up with the balance between electricity and gravity in this problem, says that if you increase the masses of the objects, you're going to also have to increase the charges on the objects to maintain the balance at the same angle of 7.3 degrees. And if you look at the equation, if we increase m over here on the right-hand side, then we'll have an increased charge over here on the left-hand side. So it does incorporate that basic concept that's tied to the equilibrium in the problem and the role of gravity and electricity in the problem, that if you increase mass and increase gravitational forces, you've got to increase the charge and the electrical forces. So that makes sense too. Another thing you might check about your result and your equation that you use to derive your result is related to the units of the equation or the dimensions of the equation. As you know, on the left-hand side and the equal side, right-hand side of the equal sign in a physics equation, the units have to match, the dimensions have to match. In our equation that we derive the charge from, on the left-hand side, it's really rather simple. The dimensions are the dimensions of charge, and the units are the units of coulombs. On the right-hand side, it looks much more complicated. We've got a variety of terms with a variety of dimensions and units. We've got R has units of meters. We've got M, units of kilograms. We've got G with units of meters per second squared. We've got K, the Coulomb constant, that has units of newtons meters per second squared. And we've got a theta. Theta is actually unitless, dimensionless. We can check that the equation's dimensions or units match on either side of the equal sign. Now, I'm not going to do this for this equation right now, but I have done this for this equation. And if you plug in on the right-hand side the dimensions of R, the dimensions of M, the dimensions of G, the dimensions of K, and remember that theta is dimensionless. What looks like dimension spaghetti from the different dimensions of all those terms actually trickles down to have just the dimension of charge. And that kind of verifies that this equation looks valid from the perspective of units or the perspective of dimensions. Finally, I wanted to make just some general remarks on problem solving and general remarks on the value of problem solving. So, as you know, I am no psychologist. I am no therapist, but I have heard, I do understand that as humans, we build mental models, we build mental pictures of our surrounding world to try and understand the surrounding world. So those mental models of mental pictures, they kind of incorporate our perceptions, our interpretations, our understandings of all sorts of things. And those sorts of things range from, how nature itself works to how, say, people behave. When we come to physics class, we're bringing with us to physics class our individualized models for how nature works, for how physics works. Now, some of those physics conceptions may well be correct. And then others of those physics conceptions may be incorrect. And one of the things we can get out of, one of the things we can learn from problem solving is to validate our correct conceptions of physics and to correct our incorrect conceptions of physics. So that's one of the big goals of problem solving in physics. And it's one of the big goals of problem solving in real life too. Now, if a problem is simple to solve, I would argue that that problem is not really a problem. If a problem is simple to solve, you don't learn much from solving that problem. If a problem is simple to solve, you already knew what you could learn from solving that problem. The important problems for me, the important problems for you in physics are the problems that you have to struggle, that you have to persevere to solve, because those are the problems that lead you to alter or change or deepen your understanding of nature. Those are the problems that correct your misunderstandings. Those are the problems that correct your misconceptions about things. So solving physics problems does involve some hard work. It does involve some persistence. But that hard work and that persistence is ultimately correcting our misunderstanding, correcting our misconceptions of how nature works. And that's important in physics class. It's important in our everyday life with everyday problems. And so that's one of the great values of physics problem solving.